Okay, great. Yes, let's confirm the recording. Oops, sorry. That's in the screen. Okay, perfect. So I think we are on time. Yes, I can start now. Let's see whether more people are joining us. Let's go back to the room chat. Great, okay. So hello everyone, welcome to our second lecture. So I hope you are well and you are having a great week. Today we will continue to discuss data preparation. Last week, as you know, we made an introduction to Christian methodology framework. Okay. So these are the steps that we are going to focus on in the upcoming weeks. And during our workshop this Monday or Tuesday, depending on the session you're attending, we discussed data understanding and then data preparation. We also implemented several techniques. So today I'm going to continue to discuss data preparation, and we will learn some other techniques that we perform at this step. And in the workshops next week, we are going to test those methodologies using Python. Okay. And if we have any time left off after this data preparation step, I may make an introduction to modeling, but it depends how we are going to go today. Okay. So let's check the learning objectives of this particular session. So today I'm going to first discuss sampling strategies. At the end of this lecture, you will learn some of the well-known sampling strategies used in data science. Then you will also learn encoding that we apply for categorical data. I will explain the reasons of this practice, and we will discuss some different methodologies used for encoding. Then we will focus on data partitioning. We will learn how to design our training and test sets so that we can start thinking about how we can build our model and also how we can evaluate it. And finally, we will discuss one of the most important problems in data science, which is known as data imbalance problem. We will learn how to handle this problem in data mining projects. And as I mentioned, if we have time, we will make an introduction to modeling. Okay. So let's begin with sampling. Due to advances in data generation, data collection, today data sets of sizes of gigabytes, terabytes are very, very common. And in many real-world projects, data sets can be extremely huge. And let's say you can think of, let's say, 1 million customer transactions, or if we consider the financial institutions like banks, that example we gave this during the workshop, fraud prediction, there are lots of transactions happening every millisecond. So the data itself is very huge, and processing this amount of data can be very costly. It requires, first of all, equipment like hardware, software. It requires also people. So it might be very, very ineffective to actually process huge data sets. So for that reason, what we do, one way to analyze these data sets is to take a sample from it. So we call this technique as sampling. Overall, we select a subset from the entire data set, and this is known as sampling. We use this subset to draw insights and also to build our model. Okay, so we don't work on these huge data sets. We work on a sample of a data set when we have a huge data in an organization. So how this selection of this sample is important is that it needs to actually represent the entire data set we have. So overall, machine learning models are going to learn from your data. And if your data do not represent your problem or your entire, let's say, customer domain, entire transactions, then that sample will be misleading when we build our model. So representativeness is very, very important. When we take a sample, we need to make sure that it represents the entire data set, or let's say our entire customer domain or entire transactions. If it is a medical, let's say, diagnosis data, it should represent our patient's domain entirely, so that when we build our model, it learns from it effectively, and when it makes a prediction, those predictions actually will be solid. Okay. So there are various sampling strategies. We are going to discuss two of them: random sampling and stratified sampling in this lecture. But as I mentioned, there are lots of different techniques that you can explore. These two are the most effective ones, and mostly used ones in practice. So let's start this representativeness example. First of all, I'm going to use my pen. What do I mean by representativeness? So let's say this is our customers. Okay. Let's say this is again telecommunication example. We would like to predict churn, and we know that there are different customer segments in our entire customer set. So there are some high income earners. Let's say these are high income, the purple ones. This is mid income, and this is low income, and let's say no income. So let's say we divide our customers into based on their income, okay? And our data set is very huge. We have a lot of customer information, and we don't want to work on that entire data set. We decided to take a sample. And this is our sample. So this is entire data set, and this part is our sample. And when we take a sample here, we have high income, mid income, low income, but we don't have no income customers. So if we use this sample to build our machine learning model is not going to learn about this no income customer, and it will not make a good prediction about whether this customer is going to stay or leave in the future. So this sample is actually not representative. In our entire data set, we have these 4 different groups, but when we take a sample, we fail to represent no income customers, and this is a problem, okay? So in sampling, the most important thing is representativeness. So we said that there are 2 techniques we are going to learn, random sampling and stratified sampling. We will also learn how to implement these during our workshops, but let's first discuss what are these techniques and how we perform sampling. So let's start with random sampling. And here I have an example from medical, let's say data analytics project. We have patient data. So these are our patients, okay? We know the patient age, we know systolic blood pressure, diastolic blood pressure, and the last column shows whether a medicine would be effective or not. So whether medicine or drug this patient is taking effective or not. So no means it's not effective, yes means it's effective. So in random sampling, we randomly select a record for our sample. The whole process is entirely random. We don't check any information about the patients when we sample it. So we don't check their age, we don't check their blood pressure, or we don't also care about whether the medicine is effective or not. The whole process is entirely random. What do I mean? Let's say I would like to take a sample, half of this data set. Okay? So I don't want to work on the entire data. I would like to take half of it. So whole sampling is like tossing a coin. We randomly decide whether to select the first record or not. So we, let's say, toss a coin. If it was head, we selected it. The second one was head, we selected it. Third one was tail, we didn't select it, so on and so forth. So we don't care about any information about the patients. We randomly decide whether to include it or not. We just generate a random number, and if that random number is less than 0.5, we select it. If it is greater than 0.5, we don't select it, like tossing a coin. And since this whole process is random, whenever we repeat it, the outcome would be different. And we will learn how to fix this during our workshops. It's not important right now, but overall, think in random sampling, it's very simple. Like you just generate random numbers to decide which you want to select or not. You don't care about any patient information or record or observation features. You randomly pick up samples or records to include in your new small data set. Therefore, it is generally suitable when we have a homogeneous data set. So what do I mean? In this case, if you check the effective column, here we have only one yes case that we can see. And during random sampling, we may not select it since we don't consider whether this medicine is effective or not for any of the observations. We don't care about the features when we take the sample. We can miss some of the rare outcomes or let's say female, male, if you have only 10% female, 90% male, during random selection, you may miss that rare group, okay? That's the reason it's generally suitable when we have equal distribution from different categories. And it may fail, as I mentioned, represent the items or observations, records, which are less frequent in the dataset, okay? It's effective, but it may fail when we have imbalance between different groups. So for that reason, another technique has been proposed, which is stratified sampling. And this actually helps us to represent the different groups in our data. What we do, again, we have a small example here. I'm going to explain over the example. Let's say this is our complete data set, and each color, assume that represents different customer groups. So we have orange ones, maybe these are, let's say, old customers. Green ones are the mid-age customers, and blue ones are the young-age customers. So in order to make sure we represent each category in our sample and we protect the proportionality between these groups, we first divide these groups to different, let's say, strata. We call them strata. You can assume it's like a group or cluster. Based on the, let's say, you define according to which category you are going to do the split. We call this strata, and then at each group, we include those corresponding customers. So here we all have old age customers, these are mid-age customers, and these are young customers, okay? So after we generate these subgroups, then we take a sample from each group. This will make sure that we represent every category in our data, and we also protect the proportionality. So what do I mean? In here, let's say 1, 2, 6, and we have 12 old customers. Here we have 4, 8 mid-age customers and 4 young-age customers. So overall here we have 24 customers in our data, okay? And half of them are old, 8 over 24, 30% of them are mid-age, and then the remaining, so half of it, 20% is young age, okay? And you can see the proportionality. So mid-age is twice of the young age, and old age is 1.5 times of the mid-age. So when we take the sample, here we protected proportionality. So here we have 6 old age customers, 4 mid-age customers, and 2 young age customers. So proportionality in the entire data set has been protected during stratified sampling. So in other words, it actually represents the entire distribution in our customer domain, okay? So that's the advantage of stratified sampling. If we have heterogeneous groups in our data, it can help us to protect that proportionality, and also it can help us to protect the representativeness of the entire data set. Okay. So let me see, there's one question. Even with random sampling, we perform data cleaning before fetching out the sample? No, we first take the sample. You don't want to clean 50 million of records, right? If your whole data is very big, you don't want to spend any time to fix those entry errors or fix those, let's say, missing values. There are different things that you can do, but we first take the sample and then work on that sample and apply preparation steps. So sampling is generally the first thing you do, so that it is quite effective, the processing the data. There's another question: are there disadvantages of stratified sampling? So disadvantages of stratified sampling, if you have lots of different categories, then the whole process is a little bit complex. But overall, compared to random sampling, it's not disadvantageous. Okay. So if you have any questions regarding sampling, please post. We can discuss them at the end of the lecture. Okay. So now let's discuss another preparation step, which is known as data encoding. So most machine learning models actually rely on, as it is written in here, rely on mathematical operations. Actually, those predictions based on some calculations, like we multiply the matrices. As you see in here, we calculate the distances between different records. So it's all mathematical. The reason of data encoding is that when we have categorical data like gender, female, male, or let's say in the previous example, we have high income, mid income, low income, no income customers. So these categories are represented not by not by numbers. They are represented by let's say, by using textual information, right? So female, male, high income, low income, mid income. So some machine learning models struggle. Actually, if they use mathematical operations, they can struggle to work with these categorical data. They can't multiply female, male information, or they can't multiply those customer segmentation information. So they can't work with text labels. Even we save them as categorical, they can't process it if they work with mathematical matrices or distance calculations. So for that reason, we need to change those categorical features somehow. These machine learning models can handle them before model building. So that's the reason this is in the data preparation step. We can't build the models, not all of them, some of them based on mathematical formulations. We can't build them. For those models, we apply data encoding. And how do you know whether you need to apply or not? Actually, when you import your data or when you load your data to a machine learning model, it's not going to work. It will give an error. In Python, you will receive an error saying that model is not going to process your data. So in order to alleviate this problem, we apply encoding. There are different encoding techniques. Basically, what does it do? It converts categories into numbers so that machine learning model can handle it. And we also actually keep the relation between the categories. So for instance, you may remember we divide the data into nominal, ordinal. In nominal, we don't have ordering like female, male. In ordinal, we have ordering like high income, mid income, low income. So we will apply encoding techniques, try to keep this relation and also help machine learning models to process that data. Okay. So there are two types of categorical data. Encoding is applied to categorical data only. In numeric, we don't have any problem, like height, weight, those are numeric values, either continuous or integer. Models can handle it. It doesn't important. But if it is categorical, then we apply this encoding. And based on what is our data type, whether it's nominal or ordinal, we can apply different encoding techniques. So let's start with the nominal ones. So nominal, just remember, nominal means we can't order the categories like color, gender, language, nationality. One of the techniques known as mostly commonly used as one-hot encoding, this is also called dummy encoding. This will help us to actually change or represent nominal variables by using numeric values. So here we have a kind of small example. Let me explain over it. We have, let's say, in our data set, different entries, and as a feature, we keep the color. So red, yellow, blue, and green. So we have 4 colors here. So this is a nominal variable. We can't order it, and we are going to represent it. What we do, we actually generate a column for each color. So these are currently in the observations. For instance, let's say this is ID1. We have red color, for ID2, yellow color, so on and so forth. Now, what we are going to do, we are going to have this whole color feature categories in our data set as a column. So here we have red, yellow, blue, and green. So each category becomes a column. Now, then it's easy. We just use binary numbers, 0 or 1, to actually mark whether that particular entry represents that color or not. For instance, if you check ID1, which is red, we have 1 in red column, zeros in the rest. ID2 is yellow, so we have 1 in the yellow column, 0 in the rest. Third one, again, red, we have 1 in the red column, rest is 0. So this is called kind of dummy variable generation or one-hot encoding. So what we did, we actually had this whole column, a whole feature and categories represented as separate columns in our data set, so that for each entry, we can generate numbers, ones and zeros, and these numbers are numeric. Machine learning models can handle it. Okay? And so it is a nice way to do this, but it has some disadvantages, one-hot encoding. So first of all, sometimes we omit one of the categories. This is called dummy variable trap. This is generally a problem for the linear models. So what do I mean? Here, as you see, if I know that if ID1 has 0 in yellow, blue, and green, that means it has 1 in the red column. So I can actually identify the value of a particular observation looking 3 columns. I don't need to use all 4 columns. I can use 3 columns in my data set to predict the one for the 4th one. So if I, for instance, drop the green one, let's say we drop this whole column altogether. If you check ID5, we have 0 for green, 0 for yellow, 0 for blue. That means it is actually a green. Since each row, if I go back to the previous case, each row adds up to 1, right? My each record could be one of the categories. Since this is a categorical data, I split the whole data set into categories, and each record belongs to one category. So these 4 colors here are dependent on each other. We have dependency. And when you build the machine learning model with this dependency, the linear models like linear regression, logistic regression is going to fail. The coefficients that you will get from your model, we will discuss these details later on. So you don't need to worry about the technical details right now. But the whole prediction at the end is not trustable. It may produce unstable model, and this is known as dummy variable trap. So what we do, you can randomly drop one of the columns. That's just easy, okay? So which column is not important. You can either drop red, yellow, blue, or green. It doesn't matter. If you have 4 categories, that means you are going to add 3 columns to your data set to prevent this problem. Some machine learning models, not the linear ones like neural networks, random forests, decision trees, they don't affected by this dummy trap. So it's just a problem for the linear ones. But since you can easily predict the outcome of one of the categories based on the rest of the tree, it's better to drop one of them to prevent the problem from the beginning, so that you can safely actually build a linear model to check whether it works well or not in your particular case. So this is one of the problems, but it is easier to handle. The second problem with one-hot encoding is that in some of the categorical variables, we may have lots of categories. Like for instance, if we have 10 categories, that means in the nominal variable, we are going to add 9 columns. Due to dummy trap, we drop one of them. We will add 9 columns. So if you have, let's say 20 categories, you are going to add 19 columns. So your dataset size is going to increase. This may increase the model complexity, computation time, and it may affect the performance of the model. So although it's mostly suitable for nominal variables, when we have too many categories, we can actually consider other type of encoding techniques. So one of them is frequency encoding. This is used for categorical variables with many categories, like high cardinality. Let's say you have 20 different categories, not just 4 or 3. So we actually don't add columns. We find a much more smarter way to represent them. Again, let's focus on our small color example. Now we are going to actually apply frequency encoding based on how many times we see that particular category in our data set. So if I write it down here, for red, we have 2. This is 1. This is second. Overall, we have 6 records. 2/6. For yellow, we have 1/6. It is the frequency. So we have only one yellow. For blue, again, we have 2 records, 2/6. And for green, we have 1 record here, 1/6. So frequency encoding checks the frequencies of each category and then replace that category with the frequency. So from now on, whenever I see red, I'm going to replace it with 2/6. For yellow, 1/6. Red, 2/6. Blue, 2/6, sorry. Green, 1/6. Blue, 2/6. Okay? So this will help us to not to add any more columns, represent the colors by numbers, and keep the same column. So data size is not going to increase, it will stay the same. And we will represent each category based on its proportion in the data set. And this will help us to get the numeric numbers for those categories. Okay, so what is the disadvantage of this now? Disadvantage of this is that original data, we don't have any ordering between these categories, but with frequency encoding, we actually impute some artificial values which may affect the performance of the model, which may mislead the model depending on the data mining problem you have. So as you may remember, in our last workshop, I mentioned that which technique is the best. It changes based on the problem you have, based on the data set you have. So I can't say one-hot encoding is better than frequency encoding or vice versa. Definitely, if you have only a few categories, 2 or 3, you can use one-hot encoding. It's much more safer. But as your data gets bigger and as your number of categories increases, one-hot encoding can be problematic. So frequency encoding can work better, but we can't know without testing it. Okay. So let me check some questions before I move to another encoding technique. Let me check my time as well. Okay. So one question, this is related to sampling. I will take it at the end. Let's check for encoding now. With encoding, if for the high income, mid income, would 10,000 to 5,000, so if we have kind of intervals, it is for ordinal encoding. I will come to that one. So currently we are discussing a nominal one. Okay. One question for frequency encoding, how we know if ID1's color is red and so on. I think you mean this part, right? For instance, if let's give an example again. So let's say, in order to prevent this dummy trap, the dependency between columns, we drop red one. And your data set includes yellow, blue, and green. So for ID1, we have 0 for blue, 0 for yellow, 0 for green. But overall, our color feature has 4 categories in our original case. So in the entire, let's say, real world or entire data set, we have 4 categories. And if in your data set, ID1 has 0 for yellow, 0 for blue, 0 for green, that means it has 1 for red. Even red is not represented in your data set, since we know originally we have 4 categories. If the 3 of them are 0, that means the remaining one is 1. So that's how we know whether it's red or not. So that's the problem actually with dummy variable trap. So there is a dependency between columns. We can actually predict the value of one of the column by looking the remaining 3. Okay, so we don't need to have 4 columns in our data set. We can identify one of the values by checking the rest of the 3 columns. I hope this is clear now. For the frequency encoding, we have a question. So in frequency encoding, we first check the entire data set, okay, and then identify the frequencies of the categories. So at this stage, we don't check the records. We divide as you see, we have 6 records in here. 2 of them are from red, 1 of them are from yellow, 2 of them are from blue, 1 of them is from green. So you calculate these proportions by checking the whole data, and then you do marking. And then you go to your data set line by line. You go ID1, you see red, then you check the frequency. Okay, red should be 2/6. I will change this from red to 2/6. Then you go to the second record. You see second record is yellow. You go check the frequency of category yellow. It is 1/6. You replace yellow with 1/6. Okay. So we calculate the proportions based on the entire data set first. And then once we identify these proportions, whenever we see red, we replace it with 2/6. Wherever we see yellow, we replace it with 1/6. I hope this is clear as well. In case for several colors, we have the same proportions, how we can differ them. So if, as you see here, red and blue is both 2/6, we replace both of them with 2/6. So this doesn't mean now ID4 is blue or ID1 is red. We lose that information. We don't protect the original category information. So that's the reason frequency encoding could be problematic, since you do not reflect the real data. You apply encoding based on the frequencies of that category appears in the data set. But instead of working with a huge complex data set, which may actually result in or lead to much more problems with one-hot encoding, this is one way of solution. There are different encoding techniques. Instead of checking the representation in the entire data set, they check the relation with the some other columns. But overall idea between one-hot encoding and frequency encoding is that in one-hot encoding, we add too many columns. Model becomes too complex, and which may lead to some problems, which we are going to discuss in the future lectures. In order to alleviate this, we just want to add one column, and we use the representation in the entire data, frequency in the entire data. Okay. So now I need to move on. We can discuss your questions later. Another one is for ordinal variables. So as you may remember, in ordinal variables, we have ordering between the categories. So let's say we have customer data and we keep customer satisfaction. Dissatisfied, average, and satisfied. So we have this ordering in between. So for ordinal encoding, we assign numbers based on this order. So dissatisfied is 1, average is 2, satisfied is 3. So satisfied is greater than average, average is greater than dissatisfied. So you assign these numbers to protect the order between the categories. And then wherever you see average, average will become 2, dissatisfied will become 1, and satisfied will become 3, so that you can represent your categories with the numeric values. Okay, so in this case, important thing is to protect this ordering. You assign numbers based on this ordering. Which number to assign? So it doesn't actually, since this is a synthetic replacement, we generally start with 1, 2, 3. So we don't assign 1,000, 1 million, 10 million. If the differences is huge, then this may mislead the machine learning model, since they are going to work on these numbers. Mostly in the literature, we use this type of assignment, but there is always risk, right? Since you don't represent them as in the entire data set or in real world. Okay. So a word of caution, encoding may increase the size of the data. We discussed this, especially one-hot encoding, which may deteriorate the performance. Therefore, there are different encoding techniques. And if there are huge number of categories in a variable, instead of using directly frequency encoding, maybe you can group some of the categories before applying the encoding techniques, and then maybe you can apply one-hot encoding. Let's say you have 20 categories, but somehow you find a linkage between those categories, and then you decrease them to 4, and then you can apply one-hot encoding. That means you are going to add only 3 columns and you can perform the operation. On the other hand, another important thing, so as I mentioned, some of the machine learning models struggle with the categorical variables. Decision trees, on the other hand, can handle categorical variables, so they can work with female, male, or red, blue, yellow type of categories. So that means you don't need to apply encoding to the this machine learning models, which can work with categorical data. So you need to first check whether the model that you would like to build can handle the categorical data. If that is the case, you can go ahead without applying encoding. You can work with machine learning, work with your data set entirely. Okay. So another data preparation step, which is actually very, very important for modeling. Before model building, we need to complete this step. It is data partitioning. So when we built our models, we were discussing this in the past 2 weeks, if I count this week as well. Our model is basically learning from the data set, right? We have a historical data, raw data, like in the telecommunication case, we check previous transactions, customer calls, customer information, and then we try to identify whether a particular customer has a risk of leaving or whether the customer is going to stay. So we try to learn from the data set itself. And then we build model, and we need to somehow evaluate that model, right? So we need to test whether this model learned well enough or not. If we use the whole data set to build the model, then that model is going to learn from that whole data set, then we will not have anything to test it. If you test the model on the same data set that is learned from, then the results will be misleading. Since these machine learning models are quite smart, they can learn very well. If you use the same data, both for building and testing, then your model can perform really, really well on the same data. But when it is implemented in the real world, it may fail. Okay, so you need to have a data set which is not used during model building stage. So this is really, really important. We call this data set test set. So what we do, we actually divide our whole historical data into 2 groups. One group will be used for model building. We call this data set training data. And the other group will be used for model testing. We call this data set as test data. Okay? So both data sets is actually coming from our historical data. We divide them into 2 so that model use one of them to learn, and then we use the other one to check whether our model is performing well or not. Okay? So to evaluate the model performance, we need to test it on unseen data. Okay? This is really, really important. You shouldn't forget about this. So let's see an example here. We have the same patient data. Let's say eventually we would like to predict whether the medicine would be effective or not on a particular patient when we treat that patient with that medicine. So we know the age of the patient, blood pressure of the patient, and then we also see in our historical data, so this is historical data, whether this medicine was effective or not. So our aim is to make a prediction on the medicine effectiveness. We are going to build the model. This model is going to check the relation between these 3 custom patient-related features and whether that medicine was effective on that patient or not. And then we are going to check whether those predictions would be actually correct or not. So what we are going to do, we are going to split this available data into 2. This split is performed by random selection or stratified sampling as well, stratified selection. So we will learn this during our workshop, how to perform this split. But basically, we are dividing our data set to training and test sets. So randomly, or based on some rules like stratified sampling, we assign records to training data to test data. So at this stage, the important thing you should see that there is no overlap in between. So the first one goes only to training data, second row only goes to the training data, third one goes to the test data. So we don't see this third row in the training data. We don't see it. It's just in the test data. So these data sets are distinct from each other. There is no overlap. Okay. By random chance, you may have a patient which has the similar, let's say, age, same blood pressure, let's say same outcome, but this is very rare to have exactly the same record or similar patients. Overall, here we have 9 records, 3 of them goes to the test set, 6 of them goes to the training set. Then we use training set to build our model. So this is just for model building. Model is going to learn. And then the rest will be used for testing. Okay, how our model is performing. Given this age, blood pressure, our model make a prediction whether the medicine would be effective, and then we will check with the historical result whether it is a match or not. So we will discuss this in more detail in the upcoming lectures. So at this stage, the important information you should know, the purpose of splitting between training test sets to have a data set to build your model and to have a data set to test your model. So this is kind of another illustration. Generally, we can split it based on 80-20% distribution. In the most of the literature, you can see 70%, 30%. So how you define which person to use? It depends on the data size. So the reason we allocate more data to training is that model learn better. So let's say if you have only 1,000 records, you don't want to split it 500 here, 500 test. So your model should learn from the data. If you give less training data, it may not learn well. That's the reason we generally allocate higher split, higher percentage to the training data, less percentage to the test data. But if you have a huge data set, then you can split 50-50. It's totally fine. But in general, when you check the literature, 70-30 is the most common one, or 80-20 if you have a little bit larger data set. Okay, so a question for you. You can type to the chat. What do you think about this? It is true or false? Okay, good. You get the main message. It is false, right? So we can't use the same data for both training and testing. Otherwise, model is going to be tested on the data set it is learned from it. For instance, if I give you the exam questions, right? You will study those exam questions. You will know the perfect answer. And when I test you, you will all get 100 marks, which is great for you. But it may not be great when you go out to the real world. If you see something different that you haven't been tested, you can easily fail. Okay, so that's the reason training and test sets should be separate so that we have the correct understanding whether our model works well or not. Or, for instance, you've seen the test results and they are very satisfactory. You implement the model later, you scrap that model. If you see any problems, you can go back even to data preparation and try to improve the model performance. So this is false. Okay, great, we are on time. So now I will take your questions at the end since we are at the last topic, and then we will discuss your questions, okay? So I'm going to now introduce you one of the most well-known problems in data science, which is imbalanced data. So in many real-world practices, we don't have a good balanced distribution between the outcomes. For instance, fraudulent cases, we give several examples from that. In bank transactions, fraudulent cases are quite small, like there are lots of transactions happening, financial transactions happening in every millisecond. Most of them are legitimate. If you consider how many times you used your card in the past week, you had lots of transactions, all of them are legitimate, but there might be some fraudulent transactions in the system and they represent it very, very rarely. So it may happen maybe once in a once a year or maybe once in a lifetime. So these events are really, really rare, but you have millions of records. So your data is imbalanced in terms of the outcome that you would like to predict. So we call this class distribution. As you may remember, I use class terminology several times. We are working on classification problems. We are trying to predict the outcome. So outcome of the class, in this case, is fraud, not fraud. And in our data set, we have huge legitimate transactions, so not frauds. We only have few fraud cases, okay? And most of the time, predicting these cases are the interest of the business. Like if you consider the churn prediction, they would like to identify the customers who are going to leave. If you consider cancer prediction in healthcare, we would like to identify those rare, let's say, diseases early so that we can act on it. So most of the time, rare events are the outcomes that we would like to predict. And this is a problem for the machine learning models. They can generally work well when the classes are balanced. When we have this imbalance between the classes, between the outputs, they generally tend to learn from the one which has the dominance in the data set. So if I use this data directly, it will focus on legitimate transactions. It will learn more from the legitimate transactions. Then the prediction about the fraudulent ones would be problematic. So this problem is known as data imbalance problem. So why this is a problem? Let's think about this. Assume that we have 10,000 insurance claims. Only 100 of them are fraud, the remaining 9,900 not fraud. You built your model, and these models, when we built them, as I mentioned, those are mathematical models, they have an objective. So they would like to achieve something. Generally, that objective is accuracy. So when you build the machine learning model, the aim is to have the highest accuracy. And if I predict everything as not fraud, let's say I have a very dummy model. This model predict everything as not fraud. I give them these 10,000 transactions. All predictions are not fraud. What would be the accuracy? Accuracy would be 99%, right? If I predict everything not fraud, then 9,900 of them would be correct. Overall, I made 10,000 prediction. My accuracy would be 99%. So I can identify those not frauds, 99% accuracy, but that means I'm going to miss all of these fraudulent ones. So that model is actually useless. Since I'm going to miss those fraudulent transactions, insurance claims, it will cost the company huge. I missed all of those. Even I have 99% accuracy, it is useless. So that is a problem. The model should learn from these fraudulent cases, but if we give this data set, it will fail, since it will not going to learn from these minority classes, okay? So what we do for this case, we need to somehow help model to learn from this. We need to increase this minority class visibility in our data set. There are several techniques. We will discuss two of them and in our lectures, but I will give you some references to check the rest. First of them is oversampling. So in both techniques I'm going to discuss today, the aim is the same. We would like to increase proportion of these so that model starts to learn from it, okay? In oversampling, we basically duplicate the instances from the minority class. So we add copies of the fraudulent transactions. We don't create new data, we just copy it, okay? So that it has a higher proportion in the entire data set, in the data set that we are using for model training. The other one is undersampling. Again, aim is the same. We would like to increase the visibility of the minority class. That means we are removing records from the majority one. So we remove transactions from the not fraud legitimate cases. Overall, we have here, for instance, in the training data, let's say we have 9,900. I decrease this to, let's say, 6,000. Okay, so you remove records. In this one, overall you have 100 records in the training data, let's say, and we increase it to, we double it to 100. So currently don't think about the proportions. I'm just trying to give you a perception is that in oversampling, we just copy it. In undersampling, we remove from the majority, but overall aim is the same. We want to increase the visibility of the minority class, fraudulent transactions. So let's see the example of oversampling. Here, again, this is an example for the medicine case. As you see here, we see one case from the medicine effective. There might be more cases, so we don't have the entire training data here. So this is training data. Then what we do, we copy this minority class. We select the minority class. We generate copies of it. As you see in here, these are exactly the same. Same patient. We increase the visibility of that minority class. And then we use this data for model building. So that's the reason it is used for the training data only, okay? Your test data should reflect the reality. If in real world we have only one fraudulent transactions out of 100, your test data should reflect that. Our aim is to teach model to understand those minority cases, okay? So model learn from the training data, therefore we implement this step to only training set, not to test set. Test set should reflect the reality. Let's see undersampling. So for the undersampling now, we randomly pick up records to remove from our data set. These records are from the majority, all no cases as you see. The aim is to increase the visibility of the yes cases. This is our undersampled data. Now we have less known cases compared to the initial training data. Again, we use this new training data. This is training only for model building. And we use the real test data for model testing. Okay, so we are almost at the end. Then I will check your questions. So there are some notes, important notes. We don't need to have perfect balance. So if you consider fraudulent transactions, 1/100 claims are fraudulent. That means you need to heavily copy the same record over again and again, and it may actually might be problematic. So you don't need to have the perfect balance. How do you know whether you have enough representation? That's the reason we use test set. We check whether our model learned well. If you are still not satisfactory, you go back to this oversampling, undersampling step, change the proportion, train your model again, see whether it learns from those minority cases or not. So you don't need to have perfect balance, okay? This is trial and error. We need to check whether our model is learning well enough. This is really important. We only apply to the model training data, not test data. Your test data should reflect the reality. Otherwise, results will be misleading, okay? Test data should behave like a real world so that when you decide deployment, you have the confidence to your model. If your test data do not reflect the real world, then during deployment, there will be lots of problems happening. And there are some other methods. Actually, the best one is collecting more data from those minority cases. If you can do that, that would be really helpful, and your model is going to learn from the real data, since otherwise these oversampling, undersampling is just interruption to the training data, right? You synthetically add some records and you remove records. So there are also some other techniques. So we are not going to implement them, but there are ready-made packages for that in Python, in R that you can use. One of them is synthetic data generation. So this is actually do not copy directly. It is create, oops, sorry, what happened? Let me just go back. Okay. So this is, can I use? Okay, yeah. We just generate some records based on the minority records we already have. We generate something similar, close to our original minority fraudulent cases. We are not directly copying. We are generating something similar here. That technique is called smooth, and it is generally working better than oversampling, but not all the time. As I mentioned, there is no best technique. It depends. And another thing is during model building stage, you can actually help your model to learn from those minority cases. You can actually penalize the model if it misclassifies that fraudulent transaction. So during model building, we can also induce some penalty to the model if it focuses on the, let's say, legitimate cases and misses those fraudulent cases. So we will see how to do it during our workshops. And finally, a word of caution. This is our imbalanced data. As you see, in undersampling, we remove records. Now here we have less data. That means undersampling is going to remove information. It is generally better to use when you have a large data set. Otherwise, your model may not learn well from those majority cases as well. Oversampling, on the other hand, is just replicating. Or even smooth, you generate synthetic samples which may not represent the real world. So it doesn't create new information. The best thing is to always go back and collect data, but most of the time it's not possible. So these techniques always has advantages, disadvantages. You need to apply and see how they affect your model performance and then select the best one to use. Okay. So let me see. Oops, I'm here. Okay. So now last few questions and then I will conclude the class, take your questions. So what do you think about question 2? Is stratified sampling more effective for balanced or imbalanced data sets? So the question might be a little bit misleading actually. Maybe I should ask for the other way around. So stratified sampling, as you may remember, our aim is to represent. It will work well both on balanced and imbalanced data sets, but for imbalanced data sets, stratified sampling is better compared to the random sampling, right? Since in stratified sampling, we make sure we represent those minority cases. Maybe this question is a little bit misleading. So overall aim, or my overall plan here, was asking whether we should choose stratified sampling for imbalanced data sets or not. Most of you say imbalanced, that's good. If you misunderstood my question, sorry, it's my terminology. But overall aim, when you have an imbalanced data set, random sampling is risky. You can easily miss that rare class to represent in your sample. Okay, another question. The reason for partitioning is to evaluate the model on data not used in the modeling process. Is it true or false? Okay, good. I see lots of truths. That's good. I asked this question before, but now you may realize that this is really, really important. Partitioning should be performed first and then model building. Our model shouldn't learn from the test data. That is called data leakage, and it's a really, really big problem. Test data should be unseen so that we evaluate the model let's say, fairly. And the last question. Given the data set is imbalanced, when should we apply a data balancing technique, A or B? I am receiving mixed answers. So this part is important. Let's go back. So our model is going to learn from the data. If I go back to here, and then we are going to evaluate it. Evaluate it on the test set. So this test set should reflect the reality. If I apply data balancing before partitioning, that means my test data is not going to reflect the real world anymore. So that's the reason we partition the data and then we apply balancing to the training set, data balancing if it is required. Test set should reflect the reality. Okay, that's really, really important. The idea of having a test set is to see your model performance on the real world. If your test set do not reflect the real world, you can't be sure whether it is ready for implementation or not. Okay. So I hope now this is clear. I will take your questions. And if you want to leave, please feel free to leave. But I will go back to the chat and then check your all questions from the beginning. Okay. So yes, now I am in here. I am at the beginning. So I responded the random sampling question. Okay. One question, isn't it possible to perform a data analysis with an entire population instead of just